Okay, let's look at the properties of convolution or properties of LTI systems. The first property is commutation, which means convolution operation is commutative. What does that mean? It means if this is my input and this is my system, this is equivalent to say this is my input and this is my system, right? So if I know the form of xn, something like this, and I know the form of hn, whatever, then if I reverse the two, basically I make this as my input and this as my LTI system, then the output yn will be same, doesn't matter. Okay, now how do we prove it? The proof is pretty straightforward, just from definition we can say. Okay, let's start from here. X convolved with h, and this is equal to, as you know, xk h of n minus k summed over all k from minus infinity to plus infinity. Now I can do a substitution, a change of variables. Let n minus k is equal to L. So let us define a new variable L, which depends on the variable k. N is anyways fixed, so we need not worry about that. So this becomes summation over L now from, okay, plus infinity to minus infinity, which does not matter in discrete domain. So x of k becomes x of n minus L, and h of n minus k becomes h of L. So this is equivalent to summation over L, h of L, x of n minus L, just I'm reversing the two, which is equal to h convolved with x at the nth time instant. So hence proved. Right. Let's look at another property of convolution, which is distributive over addition. Okay, what does that mean? I have x convolved with h1 plus h2. This can be written as, by definition, summation over k, xk, and then in the bracket h1 plus h2 n minus k. This can be simply written as summation over k, xk, h1 of n minus k plus h2 of n minus k. And now I know summation, this product is distributive, and the summation can be taken inside. Summation over k, xk multiplied with h1 of n minus k plus, again, summation over k, xk multiplied with h2 of n minus k, and this is very clearly equal to x convolved with h1 n plus x convolved with h2 n. So pictorially I can see it like this. If I have a system h1, another system h2, and I am adding their outputs, basically. If I add the two, so that's what I'm doing here. X pass through h1 and x pass through h2, and I add the two outputs to get my y of n. Then this is equivalent to x of n h1 plus h2 I of n. Okay. Next thing is property of associativeness. That this operation of convolution is associative, which means whether I do this convolution first followed by this convolution, or this convolution first followed by this convolution. Pictorially, I can see it like this. I have a system h1. I pass my x through h1. This is this part, and then this output is passed through a system h2 to get my y. This is equivalent to x passing through a complete system which is h1 convolved with h2. The output is y. Now, how do we prove this? The proof is, okay, a little bit messy, but it is very simple. Let's start from, let's say, left hand side. So in left hand side I have x convolved with h1 convolved with h2, and this whole thing n. I can write it like this. I can say this is x n convolved with summation of h1k h2 of n minus k summed over all the k's, right? And I can further open up the next convolution. So basically what I have to do is I have to replace, so I replace in the first term I replace n with k, in the second term I replace n with n minus k. So in this case I take another variable, let's say L, so I replace x with xl convolved or multiplied with summed over all L multiplied with this term. Here I have to replace n with n minus k, or in this case n minus L. So summed over k h1k h2 of, I replace n with n minus L, and minus k is as it is. Now I know that this product is, it is, I can open up this bracket. Let's say summation over k outside, h1k is outside, and I can take L, I can consider L first, which means x of L and h2 of n minus L minus k. And now consider this term. I can, so to go back, I replace L with n, and in the second term I replaced n minus L with L. Right? I have to go back to the convolution notation now. This means summed over all k. This is h1 of k as it is, times this becomes x n convolved with, I'm sorry, so this becomes x convolved with h2 at, so in this case n is n minus k, right? So n minus k minus L, and here just L. So replace L with whatever is the n, and here you replace n minus L with n, but here it is n minus k. So this is what it becomes, and this is simply h1 convolved with this thing, which is x h2 n, right? So what I have proved here is x convolved with h1 h2 is h1 convolved with x h2. Now I can simply use commutation property to see that to prove the basically the LHS is equal to RHS. So I can rewrite this as so here the RHS from here is simply x convolved with h2 convolved with h1, and the LHS was, so here I can again use commutation, x convolved with h2. So this is the same as what hence proved. Now let us consider the stability properties of an LTI system. So what is the meaning of Bibo stability? Bibo stability means my output yn should be bounded for all n if my input is bounded. So basically for all possible bounded inputs. So which means I choose any bounded input xn and pass it through the system, the output should be bounded for all n. So this is the meaning of Bibo stability. How do I see what properties my system should have so that it is Bibo stable? No problem, we will start with this. Our goal is that yn, let's start from here. My yn, so how do I write it? I can write it as convolution operation, basically h of k times x of n minus k summation over all k, right? And now I know that this is always less than or equal to sum over individual terms, which means h of k into x of n minus k. Now I know this term is always bounded. This term is always less than equal to bx. It's given here. This term is always less than equal to bx. And so this means my RHS this is less than equal to bx times summation over k h of k. Now what is this term? Now if this term is bounded, okay, let's call this as bh. Now if my bh is less than infinity, which means it is bounded, then certainly my y of n will be bounded, right? So let us call this as b of y. So y of n will be bounded for every value of n for every input x. Hence the property that, so let's go back, the property that this summation over hk modulus is always bounded, means absolute summable hn, this property implies Bibo stability, right? We just proved. Now is the reverse true? Is the reverse true? Okay, to prove the reverse, we start with Bibo stability and we try to prove that Hn is absolutely summable. Let's see if we can do that. What is the meaning of Bibo stability? Bibo stability. Now it is given that my y of n is equal to some by. Okay, less than equal to some by, which is less than infinity. Right? My y of n is always bounded. Now, okay, let's expand my y of n in terms of convolution, h of k, x of n minus k. Now this has to be true for all bounded x of n, right? This is true for all bounded x of n, and I want to prove that Hn is absolutely summable. So I have to choose. I can choose a clever. I can cleverly choose a value of xn so that so that I can prove basically that Hn is absolutely summable. That this absolute sum, this sum is less than infinity, right? Now, okay, let me choose. I want to choose an x. Choose your choose x in such a way that xn minus k is equal to h star k divided by mod of h. Now see, for any value of h, this will always be bounded. Okay, means you can say, okay, when hk is not equal to 0, and take it as 0 when hk is actually 0, just to make the definition more precise and complete. Right? So if I choose this value of x and k, then the xn is always bounded, right? Xn. So what is xn mod? This is equal to 1 or 0. So basically this is always less than equal to 1, right? For all n. Let us substitute this here. So what I get is the LHS will be equal to summation over k hk times h star k divided by mod of hk. So the numerator is basically mod hk square. So this becomes summation over k mod hk, and I'm saying that this is less than equal to, so this LHS is less than equal to by, which is less than infinity. So this means, this implies, basically we proved that Bibo stability implies absolute summable Hn. Hence, an LTI system is Bibo stable if and only if the impulse response is absolutely summable. The references for this, you can consider Oppenheim, Chapter 2, Section 4. Thank you very much.